Hello, my name is Lidia Almazán, and I'm going to introduce the article called A Numerical Study of the Navier Stokes Transport Coefficient for a Two-Dimensional Granular Gas. And my co-authors are Professor José A Carrillo, Professor Clara Salueña, Professor Vicente Garzó, and Professor Thorsten Pöschel. In this article, we present a numerical study of a two-dimensional granular system comparing the well-known event-driven molecular dynamic simulation with two different approaches for the Navier Stokes transport coefficient for the hydrodynamic simulation. These two approaches are Jenkins Richman theory, which is considered for moderately dense quasi-elastic grains, and the improved Garzó Dufty Lutsko theory, which includes the effect of the inelasticity on the transport coefficient. Previous studies of the Faraday instability for inelastic hard disks compared molecular dynamic simulation with the Jenkins Richman hydrodynamic simulation, finding a good description of the rapid granular flow. Our aim is to check if one can get a better agreement using improved transport coefficient. This instability appears when a fluid is shaken in vertical direction considering an external force like gravity. And in this video we can see the density field for the three different simulations: MD, Jenkins Richman hydrodynamics, and GDL hydrodynamics, when the Faraday instability has already formed. This happens after about 50 periods of shaking. We observe a superharmonic period dynamics where the period is twice the period of forcing. We study different quantities to analyze the mechanism of unstudied supersonic granular flow. We are representing a vertical cut of different flow magnitudes as a function of the height in diameters at a position where the maximum height of the pattern is achieved. From left to right and from top to bottom, we have represented packing fraction, internal energy, temperature, vertical component of heat flux, cooling coefficient, and kinetic energy. All of them are scaled with gravity and particles diameters. Let us draw the attention onto the packing fraction and the temperature field. At T0, the piston is going down through the equilibrium position. From that point, the GDL prediction is denser than JR, in height between 10 and 20 diameters. Then we have the dissolution of the peak, and the valley appears. After that, we have another impact with the plate forming again a peak. The maximum density in MD is smaller than in hydrodynamics. The most striking difference between GDL and JR solution is the temperature, where at large height the difference is about 1 order of magnitude. This is related with the extra term that appears in the heat flux related with the gradient of the density. All these fields are explained in detail and discussed along the paper. The perspective is to understand the role of the extra term that appears in the temperature equation and in other setups as such shear flow. Enjoy the reading.